Hey, take a second and just look around you. The real world isn't just a straight line, right? Objects curve, they arc, and they spin in these incredibly complex ways. So, to truly understand and predict how things move in 2 dimensions, we've got to unlock a seriously powerful mathematical toolkit known as vectors. Let's dive right into this explainer. We've got a lot of ground to cover, so here is our exact roadmap for conquering 2-dimensional motion. We're going to start with scalar and vector basics, move into vector addition and resolution, then we'll analyze projectile motion and its flight metrics, and finally, we'll wrap it all up with uniform circular motion. All right, Section 1, Scalars and Vector Basics, Building the Foundation. So there are fundamentally two completely different ways we measure the world. On one hand, we have scalars. These are just your basic numbers with units attached. Think mass or speed. But vectors are a whole different beast. They require both a precise value and a strict direction. You can't just say how fast an object is moving. If you want to find its displacement or velocity, you literally have to define exactly where it's going. Now, here's a super interesting exception to that rule: electric current. You'd probably think that because current clearly has a direction of flow through a wire, it's got to be a vector, right? But nope, it is actually a scalar quantity. And the reason why is pretty wild. It completely ignores the geometric laws of vector addition and just adds up algebraically, exactly like regular numbers do. Okay, moving on to Section 2, Vector Addition and Resolution, the master tools. Since ordinary math won't always cut it, how do we actually combine these directional arrows? Well, you can't just add 5 plus 5 if the forces are pointing in completely different directions. Instead, we rely on visual methods. With the triangle law, we basically just place vectors head to tail to find the resultant path. Or if you use the parallelogram law, you bring their tails to a common origin, complete the shape, and then draw the diagonal. That diagonal right there is your true sum. Now, vector resolution, this is literally like a physics cheat code. If you have a vector pointing off at some weird diagonal angle, you can resolve it, or, break it down, into its horizontal x and vertical y components just using some simple trigonometry. It instantly breaks a really tricky angled path into manageable, straightforward, one-dimensional steps. It's a total game changer. All right, Section 3, Analyzing Projectile Motion, Applying the Toolkit. Let's see this in action. Let's pose a seemingly impossible physics problem, just to see exactly how our vector toolkit handles it. What happens when you throw an object completely horizontally off the edge of a cliff? I want you to really think about the invisible forces at play here. So, the object ends up tracing this beautiful, curved path. Notice how it doesn't just drop straight down, but it also doesn't fly perfectly straight either. It curves. And that's because it is experiencing two entirely independent movements at the exact same time. It's amazing how cleanly these two motions separate. If you look at the x-axis, the horizontal motion just completely ignores gravity. Its acceleration is 0, so it just keeps moving forward undisturbed with a constant velocity. But vertically on the y-axis, it starts with 0 initial velocity and then just constantly accelerates downward because of gravity's pull. It's literally two independent, one-dimensional motions happening simultaneously. And because these two motions are tied together by the concept of time, we can actually combine their equations. If we mathematically kick the time variable out of our calculations completely, we unlock what's called the equation of trajectory. This single mathematical expression relates the horizontal and vertical displacements and maps out the exact physical shape of the object's path. Because of that math, the path of any projectile, assuming we completely ignore air resistance, perfectly mirrors a mathematically predictable parabola. Since the vertical y-coordinate is directly tied to the square of the horizontal x-coordinate, a parabolic curve is basically guaranteed. And this is huge because it allows us to precisely predict the exact impact point based on nothing but the starting conditions. Moving right along to Section 4, Projectile Flight Metrics, the Big Three. So we've thrown things horizontally, but what about oblique projectiles? Think about launching an artillery shell from the ground at an upward angle. By using just two things, the launch velocity and the launch angle, you can calculate the three ultimate metrics of its flight. By breaking things down with our vector components, you can find the time of flight, which is exactly how long it stays airborne. Then there's the maximum height, the absolute highest vertical point it reaches before gravity takes over. And finally, the horizontal range, which is the total horizontal ground distance it manages to cover. Oh, and here is a really quick practical pro tip for you. If you're ever launching something from the ground and you want to get the absolute maximum horizontal range out of it, you've got to project it at exactly a 45-degree angle. Because of the sine function in our range formula, 45 degrees mathematically guarantees you are getting the absolute maximum distance, for sure. All right, here we are at section 5, uniform circular motion, the final boss. This is absolutely our most complex application of vectors, where the direction of movement is just constantly changing. So, when an object is moving in a circle at a perfectly constant speed, you might naturally think its acceleration is 0, right? Actually, scratch that. Because velocity is a vector, a change in direction means a change in velocity. So to keep any object spinning perfectly in a circle, you absolutely must continuously apply an acceleration and a force that pulls it directly toward the center. This right here is what we call centripetal acceleration. And these angular metrics actually explain tons of everyday phenomena. We use angular displacement and angular velocity to track the circle itself. But the real magic is that centripetal force. This inward force balancing the outward motion is exactly why a speeding cyclist absolutely must lean into a sharp turn. By bending inward, they generate that necessary centripetal force to balance their outward inertia. If they didn't do that, they'd literally just topple right over. Ultimately, the interplay between an object's speed, the radius of the curve, and the pull of gravity dictates some major safety engineering in the real world. This exact math determines precisely how much we need to bank curved highway roads or elevate railway tracks. By literally angling the surface, the road itself provides the centripetal force. This lets vehicles take really fast, sharp turns safely without skidding off into nowhere. So this brings us to a final, kind of provocative thought. If simple vector components can demystify artillery arcs and dictate the safety engineering of banked highways, what other seemingly chaotic, unpredictable movements in our universe are just waiting for the right equation? The math of motion is quite literally everywhere around us. Keep questioning what you see.